particularly related to the cloud. Somehow, okay, so it looks like I got this going again. So Capital One has been working on going to the cloud for quite a while, and we had some stuff in 2013 where we were trying stuff out with private clouds. In 2015, we announced a strategy to go to move all our computing environment into the cloud, and actually it was as a AWS first strategy, so they were our primary provider. And this year we shut down the last of our data centers. We still have what we call regional hubs, colos. These are network pops. So that's now where we have a lot of our visibility resources, and we keep them there, for a bunch of different reasons. But that's how we interconnect. As we move to the cloud, we have put into place a lot of very state-of-the-art modern technologies. You name it: big data, microservices, serverless streaming data, and so forth. And together with those technologies, we put in place a lot of modern processes. We're an agile shop. We reuse a lot of code. We use APIs. We are big into open source as well. So, fits in well that we're working with Wireshark, although I don't think we've contributed anything yet to Wireshark, but maybe we will. We contribute to a lot of other open source projects. So as we're going to the cloud, one of the things that you first have to ask is, what do we have out of the box? What kind of out of the box visibility for the network especially is available? And you can get some interface monitoring. Okay, I got an EC2 instance. How much traffic, how many packets, how many bytes go through that? Okay, I've got a pipe leading into there. How, what volumes do they have there? I can get some up-down stuff. Like if I lose a load balancer, I should be able to see that. If I lose, one of my databases, hopefully it's fully resilient, and I, even when one instance goes down and I see that, there's plenty of other things there to take up the slack so that it's fully available. But I can't see the network. I don't have an idea about the switches, the routers. It's nothing that, as a customer of the cloud environment, of AWS, of GCP, of Azure, that we ever really see. So we can't see the up down status. And sometimes we can get some ideas. There's a lot of log-based information as well that goes beyond just the interfaces. So we get some flow stuff. There's access logs. A lot of the different services have their own monitoring capabilities that we can take advantage of. But when we're looking at the networking, how does the cloud fit into our monitoring strategy? When we had our own data center, we had a very full suite of network monitoring tools. But now that we're in the cloud, we don't have, we don't own the network components. Some of the pieces that connect to it, yes, but the components inside of there, no, we don't own them, and we don't have direct polling. I can't say, hey, Mr. First Hop router, are you up? And are you dropping any packets, please? And what's your CPU utilization? How's your memory stat? That kind of thing that we could do with our in-house network, in our data center, and for a wide area network, we can't do for those cloud components. So we're looking at how to expand so that we have the visibility and the correlation to be able to understand what is going on and when we have issues in the network to be able to give us the level of service that we need now that we have all of our stuff in the cloud. So I'm just going to go over a little bit about what it means to be in the cloud, and I'm not going to be sharing a lot of real details as far as how we do everything. I'm summarizing a lot of stuff. Hopefully you can understand in this cyber aware environment that, you know, we don't want to give you a lot of details, but I want to share with you enough so that you can see the levels of complexity and the challenges that we're facing. So first off, we're building a resilient environment in the cloud, and that means a resilient network to connect to it, and that the cloud itself should be resilient. So there's multiple AWS regions that we're going to. And we have our regional hubs. We have multiple of those AWS regional hubs, and they interconnect. Direct Connect is the basic building block to go into AWS, but there's similar connectivity that we have also for GCP and for Azure. So high-speed links that connect up our networking environment with the cloud providers environment, and these are done through those regional hubs, and fully resilient so that we can withstand multiple failure scenarios that you might envision. And so this is just a I think, yeah, sorry, it's for some reason it's skipping a slide. I have to hit it twice and it goes 2 slides. So inside, in this case, AWS, we're looking at, we have these multiple regions, and the providers, AWS, GCP, Azure, and by the way, we're looking at mostly a IaaS and a PaaS, platform as a service and infrastructure as a service. That's what these Azure, GCP, and AWS are providing. Similar concepts for SaaS, software as a service, but you're one level removed from there. But when we're building out inside AWS, we have multiple VPCs. The VPCs belong to an account. Those accounts have VPCs in multiple regions, and inside each of those regions, they split this up into availability zones. The availability zones are essentially data centers inside a region. So for instance, AWS has a US East 1 region, which is in Virginia, and they have multiple availability zones. I think they have something like 5 or 6 availability zones there, which are essentially data centers inside of that. And then when we're building out, then that's where we put our application. We distribute them for our different business units and the applications that run on top of that. We put those inside the accounts and the VPCs, making use of those different availability zones. So you can see the network connectivity to pull all this together is quite it would be quite convoluted, and it's hidden from us. So when we go, we connect up our VPC to our Direct Connect link, for instance, and it transparently handles all of the routing, and at least that's the intention. So here's just a real simple concept. This is this is not how it really looks, but we have our stuff shown on top, the gray bits, Capital One sites, what have you. Connected in through these multiple regional hubs, and then we have a connection into the AWS environment to the different VPCs. And note that the internet connects into AWS directly. It also could connect into the regional hubs depending upon the use cases. And sometimes AWS can talk to the different regions amongst themselves, so they can have their own conversations, or they can do that through regional hubs. There's all sorts of different ways that you could conceivably connect this. So let's see what this looks like. So if I have traffic that's going from one of our Capital One sites into AWS, then it's possibly going to be transiting that regional hub. So you can see that we have some opportunities for how we can get visibility to the network traffic. But there's more than one visibility solution there. But that gives us some unique opportunities. So if we have visibility to the traffic, at least going into there, and we'll talk a little bit later about how we expand from that, let's take advantage of a packet broker environment where we can get data, the packet data, feeding into DPI probes. And what I'm calling a DPI probe. So this is not, I'm not doing a sales pitch here. I'm not talking about any particular products, but if you have so what does DPI mean? Deep packet inspection. In fact, how deep do we need to go? Really, we need to go to layer 4. So I'm not talking about, you know, TLS and trying to look at the contents of the data. What I need to do is I need to be able to see the TCP level, the TCP level semantics. So in addition to the volumes, you know, how much traffic, how many bits, how many bytes, how many packets, how many new connections, and maybe even making sense of transactions there, I can see the response size, I can see a request and a response. But because I'm looking at TCP, the TCP semantics, I can see things like retransmissions and packet failures. You know, sending a sequence of packets and one of those packets is not there, I can detect that. I can then see it later retransmitted, I can see duplicate acts. All these different things that we do by looking in Wireshark at packet traces can be done in real time by a DPI probe. And how do we make sense of it? We need to aggregate that, aggregate it by account, by VPC, by the availability zone, by the application. However, we need to slice it and dice it so that we can make sense of that. And I put, you know, certainly by the IP address, by the port, which may map to an application, but an application is probably, you know, makes use of a lot of different things there. So the big thing here, we're looking at layer 4 to get some idea of what's happening. And when we do that, then do we get some idea of what's happening inside AWS, even by just sitting and watching the traffic in and out of there. And the answer that's come to us is yes, we are getting some good data. So here, let's look at all our traffic that's going in from a regional hub into into AWS or into a specific VPC, and we can see things like retransmission. So there's something going on there, and we can break it down and see, you know, which particular VPC. So these are, you know, and this may map to an account or inside the VPC to specific availability zones. So we now can now see, although we don't know the exact path that it's taking once it goes into the cloud, we can see the impacted pieces inside of there. And that thing about correlation, now we can make a lot of sense of that. We can do that correlation and figure out what's going on inside AWS. So not only by monitoring one particular application or, you know, many simultaneously, but I may also know something else. Well, that VPC, I know, even though I don't have visibility to 5 other applications that are inside that VPC, maybe I have some good idea of what else might be impacted, even if I don't see it. So, yeah, first thing you're saying, well, of course, it's the cloud. There's never going to be any problems because AWS builds everything perfectly. Well, it's not always the case, because obviously, if it was the case, you wouldn't be here. I wouldn't be here talking about that. So we need to take a look at that. So to do this TCP monitoring, realize it's the end-to-end semantics. So it's not, you know, it's not looking at a packet going through a router, but I have the IP address. So for instance, if there's a client talking to an application via load balancer, if that load balancer terminates the TCP connection, then if there's a problem anywhere along that path, whether it's in my, you know, the network close to the client, maybe it's his Wi-Fi connection, or maybe it's in, you know, maybe there's some MPLS or VPN or something, or maybe it's, you know, in one of these high-speed direct connects, these multi-gig links in there, or even inside AWS's own SDN. This is the piece that we don't have visibility to. In fact, we sort of don't have visibility to some of these other things. I'm just showing these conceptually, you know, not trying to give you the full details of everything, but if somewhere inside of there we start to have problems, whatever those might be, then even though we might be monitoring someplace else, if it's inside this monitoring domain of the TCP connection, even capturing on the client, I can see if there's a problem in the SDN in that part right there just before the load balancer, or even in the load balancer itself, I can detect it. I may not be able to tell you exactly where the problem is, but I know that I should know that there is a problem. So what can we do then? So where do I put this stuff? It could be an aggregation tap or switch span session inside the customer premises. You know, some of you may have gone to the session in the Zoom 2 session just before this. And they were talking about putting in these giant instrumentation environments, and it could be there. So we're going to have taps and spans feeding into it, you know, in our sites. I don't quite have that same thing. I don't quite have that same visibility inside AWS, for instance, but actually there is a mirror. So there's this, for AWS, there's a VPC traffic mirroring. It's a capability that AWS has just started providing within the last year. And Azure and GCP have similar capabilities where basically it's essentially a software-based tap span, how it's physically working. You know, they keep that information from us, but the idea is that we can feed it into this DPI probe. And I'm showing it here along this path, but it's even possible to insert that further in. So not just for the, you know, the edge of the network, but deep inside of there, if that's what you need. So by getting this visibility there, and it's packet level visibility, we can see when there are network issues, even if we're not, as I said, even if we're not monitoring the network devices themselves, we can see their behavior. And the biggest piece of that is, I'm going to call them flag packets, because we're at SharkFest, and that's what Wireshark does. If you've seen the TCP analysis.flag, that's what we're looking for. Is there a missing segment? Is there a retransmission? Is there a duplicate hack? Are there connection failures? You know, retransmitted SYNs, resets, what have you? All those things that get flagged by Wireshark, those are all the same thing that these DPI probes can be looking for. And that means that we should be able to tell in real time or near real time when we have issues in our network. Again, even if we're not, you know, if I can't tell what device it is that's failing, you know, is it a switch? Is it a connection? Is it a route that's failing? No, I don't really know. I do care, but just the fact that it's failing is enough to help me move on and get some more data. So what does this mean to us? This means we can see when we have packet loss, when we have, and we put in there in the title to this slide, these micro outages, and these are some of the ones that are pretty painful to us. Availability zone failures, interface losses, if the load balancers go down. Okay, I'm in East Coast right now. I do want to tell you, it's what, 7 o'clock now. I actually got I told you we do operational support in my team. I happen to be on call this week. I got a call at 3 o'clock this morning. There was an application that went down. It turns out it was a load balancer failure, and we were able to see that by looking at the network. And so that all this packet level stuff that we're so used to with Wireshark, we're applying it to the cloud environment. So lots of things that we can do with this, even if it's not the same visibility that we have, you know, for the networks that we directly control. All right, so you're probably wondering, you know, when am I going to see the packets? Well, here we go. So I pulled some examples. I've got 3 examples that I provided, and I'm gonna walk through them for you. Hopefully you saw in the chat that we have somewhere in there in the chat. I believe we've got a download. I put these 3 packets, and I also put a little bit of the same thing in the README file, so that you can take a look at that. Take a look at these trace files, and I'm going to give you a minute or 2 to look at them. Not too much time, because I want to look at them myself as well. But take a look at each of those files, or probably just look at the first one. I have some suggestions. I think put a display filter in for the TCP analysis flags equals 1. Mean they're true. So we have a TCP analysis flag on there. Take a look at the IO graphs. I'm not seeing very many people doing that, but it helps me tremendously, and you'll see why when you take a look at least 2 of these. It's going to be really helpful. And inside the IO graph, don't just look at packets per second. I suggest that you also look at perhaps the flags and the retransmissions. That'll give you some idea. And in the display filter, you might also, in addition to just doing overall flags, you might look at the retransmission counts as well. And then let's take a look at some other stuff. All right, so I'm going to go over and switch to my my first trace file. That's SF SharkFest 20 trace 1. I probably should have put my name or something better on it, because you're going to lose it with all these traces that you're going to be working on these 2 days. So the first thing I'm just going to do is I'm going to look at flags. I built myself a little filter button there. I don't have too many of them. TCP analysis flags. You don't actually need the equal 1, so that's fine. So that goes and grabs these things. I'm just showing the real time, and down here in the status bar we get some interesting information. Now I'm going to give you some hints. I believe on all 3 of these I only fed you with 1 TCP connection. It makes it a little bit easier. So we're not, if you were to go to look at the statistics and the conversations, it's just 1 IP pair and 1 TCP pair. Obviously, when I'm looking at this stuff, it's a lot more than that. But this helps us to understand, because we're going to look at anything like sequence numbers and so forth. This can really help there. So the next thing I was thinking that you might want to do, because I do it, is I bring up a graph. And what we have is we have some very bursty traffic, but we see that there is a period where essentially we have no data. And it may look like, let's take this one out for a second. So this is just our throughput. It may look like we have data, but if you actually overlay it with the retransmissions piece, so that's just a display filter saying tcp.analysis.retransmissions. But if you actually overlay it, all the packets that we're seeing during that period are actually they're all retransmissions. So something was going on there. And now let's go back and look and find that point in time. And let's go back. So that was about, so I tend to zoom in to find this. The zoom in only gives me 1 second resolution, but that's good enough. So somewhere around 10, 12, 31, 32 to 39 is where we need to be. Because I have this up right here, I'm just going to choose this 10, 12, and I'm going to disable that filter. And I essentially would be right at hopefully the beginning of that interval. We're pretty close. And we got these wonderful little pieces here. I don't even know what they're called over on the right side. I'm just going to click on that to get to sort of the high point. But we see 10, 12, 31. So this is, just go back. So 10, 12, 31. So that's in the middle of that outage. And if we just go look through, and 10, 12, 40. So right here, we have a big jump in time where nothing happens. This is what we're worried about. Now, before I get there, so we'll cut to the punchline later. Sometimes we get some things. I have a previous segment not captured and a TCP out of order. So this is a packets getting out of order, but it is packets getting out of order in the monitoring environment, not in the real world. Because if it was in the real world and I had packet out of order, I would have seen a duplicate ACK. Let's see some of these other things. Again, we have packet packet missing, and then it's received out of order. That's the same thing. Sometimes though we get some previous segment not captured that we don't have an out of order following that, and that's sometimes you get packet drops inside your monitoring environment. It happens. But in this case, and that's right here, this is, again, they get out of order, and and this is in the monitoring, not in the real world, because of lack of duplicate acts. And this one later on, we do see duplicate acts. So when I take a look at this, I'm looking through there. So I've got two sets of IP addresses. If you're wondering about those, I've got 10.0.1.1 and 10.0.2.1. Well, I do want to tell you those are not the real IP addresses. This has all been anonymized by making use of Trace Wrangler. So thanks to Jasper for that. These are not the real IP addresses. These are not the real port numbers. There's no data inside of here. It's all been truncated through use of Trace Wrangler, which means that I can pass these off to you. So I'm just going to say that the 10.0.1.1 is some sort of remote system that's not in AWS, and the 10.0.2 is always that's the stuff that's in AWS. And what we see is that we stop hearing from AWS at this time, 10/21/31. Let me actually, one of the things I tried to do is I'm going to set a time reference, and then instead of doing this with local time, so let's change our time display to from beginning of capture, which actually becomes from beginning of reference as well. So we're 60 seconds into it there, and then I reset that reference. So what we see is that we last heard from our AWS server at this time right here, and we next heard from it 9.4 seconds later. And in the meantime, this remote system has been sending data to it and not getting any acts back. So he then goes and sends some more and doesn't get any acts back. And then finally, 9.4 seconds into this, we get an act back. So this is this is one of these things we're terming these micro outages, where we're seeing AWS or some of our instances basically stop responding, and it's because there's some disconnectivity inside the AWS environment. This one lasted about 9.4 seconds. If we had other samples, we might have found that it might have started responding sooner. That was just, this one got through, so there was nothing that was sent to it between 5.3 and 9. So it might have been a little bit less than that. It might have been as short as maybe 5.4 seconds. But this is a good indication for this connection. The outage lasted 9.4 seconds. And actually, when we take a look at this ACK, so this is an ACK for 66357. It's actually acking this. Well, it might be this one, but it's almost certainly acking this last one that comes out here. It takes about 41 milliseconds there, which is still quite a long time, because normally we see those acts coming back much quicker. Now the impact lasts a little bit longer, but essentially within 4 milliseconds or so, we've retransmitted all of that. We've retransmitted that data, and we've caught up. But if you have applications that have sub-second response time requirements, and you have an outage lasting for essentially 10 seconds, you can imagine whatever transactions arrive during that 10-second interval would have timed out. So this still can be quite painful, even if we do retransmit that, because we're a transactional environment at Capital One. Yeah, we have lots of batch flows as well, but when we have transactional stuff, this becomes very important. Okay, let's see. I'm going to take a look at questions. Would you run? So I got a question. Would you run reorder cap on this? you could that could fix these small things, but the thing is, I'm not always sure. I don't necessarily want to do that because a lot of times we do have out of order packets that we care about that are causing retransmissions. So trying to fix them if they are real problems. So it's not something I do as a matter of course. I have to take a look at them and determine whether I can ignore them or not. But in this case, I'm looking at this. This was the outage, and in fact, let's take one step back. Why did I even look at this? And it turns out that these few retransmissions, if I took a look at these retransmissions, 25 retransmissions, and in fact, there was a smaller number just during this thing, probably only about 10 or so, was enough so that I saw there was a threshold that was violated in my DPI probe and generated an alert. That alert correlated with something with an issue that the application was seeing. Well, why do we care? It's all fixed. By the time I took a look at this, it was all better. But once these things start happening, sometimes they repeat, because if there's an issue in the hardware, now AWS, they might not care. A 10-second outage to them, they just, for whatever reason, that might not be the most critical thing. But for us, if we see some of these things, like maybe once an hour we see this happening, that might be an indicator that we need to get out of that environment and have AWS look at it in more detail. So there is something that we can do about it. Okay, so that's trace one, and if we need to revisit that, we can do that in the question and answer session. I'm now going to go and look at trace two. I think I already looked at that. Yeah. Okay, so here's trace two. I'm just going to follow that same thing. Let's just look at the flags. Well, okay, 12% flags. How many of those are shown as retransmissions? And I always look at retransmissions. That's usually the biggest indicator of problems in my environment. So I'm always going to retransmissions. And unfortunately, we sometimes get some false positives from our DPI probes. What does it mean to be a retransmission? If they don't deduplicate properly, that can cause some false retransmissions. Sometimes it might flag when just packets are missing because of when they're missing or reordered, thinking that they're retransmissions. So we need to check this thing. But in this case, it's saying out of my total of 2,800 packets, 5.8% of them are being marked as retransmissions. That's a lot. Let's take a look at the IO graph. This one's going to look quite different. All right, here we have it. Actually, sometimes it throws. Okay, it didn't do it that time. Okay, so we got the same two graphs. So if we ignore the retransmissions, we can. Somehow I clicked that twice. If we ignore the retransmissions, well, already we can see this is very bursty, and we can sort of imagine what's happening here. Rather than having you guess, because it's not quite as interactive as having you sit in front of me in a giant coliseum, I'm going to tell you what is likely happening here, which is we have some processing going on. It grabs a bunch of data and then pushes it to a server. So basically, there's a batch process. It harvests some transactional data and sends it off streaming to be processed. So 80 packets, per second, but it's all done in a short interval. So we have these bursts of data, and when we look at the retransmission, so I'm going to turn off the throughput and look at the retransmissions. We actually had no retransmissions, and it was a very clean environment. We had no retransmissions, and then all of a sudden we started seeing retransmissions. Actually, it got worse over time. I only looked at the first the first few minutes of this particular issue, and this was a very high throughput file transfer. This connection was a small piece of actually many, hundreds or thousands, I'm not sure, of other connections that were all going to the same place. And what was happening is a little bit strange. So let's take a look at this in a little bit more detail. So, 5.8%. If we were all, by the way, if we're only looking at the, if we ignore the first 30% of this, the actual retransmission rate once we get into this problem was actually closer to about 8 or 9% retransmissions. All right, let's just go. I'm just going to jump into the middle of this. Again, we're looking at one connection. I'm going to turn off my filters. Now, if I wasn't already looking at one connection, what I would have instead done is go to conversation filter TCP. This is going to be equivalent because there is only one connection there, and that's so that I'm only looking at that one connection. By the way, I know some of you might prefer to do it a little bit differently and to follow a TCP stream. In our case, we have one of the side effects of that is that it shows you all of the data bytes. Well, I don't have any data bytes. These are all sliced packets. So this is actually more efficient, and so I would suggest doing this. It also allows you to see exactly what that filter is, rather than looking at that connection ID, which is, these are coming from the actual packets, and the connection index numbers, those are Wireshark. They're just created by Wireshark. So this is reflecting what you see in your packet, so it'll be repeatable even if you have a different trace that's smaller that's looking at those same connections. All right, so let's take a look at this one again. We have a retransmission, but we see this is not the behavior that we saw before. This is not an outage. We could look at this in further detail. So one of the things we can do, let's look at 100 millisecond. Let's get it into more detail and then zoom in on that. Yeah, so we're not seeing outage. We get retransmissions when we have these spikes. If I go too much closer into it, it doesn't really help. I can do it, and then we can zoom into there a little bit more. So we even inside those 1 second bursts, where it's bursty even inside of there. But let's take a look at this in a little bit of detail. So this packet, this packet right here, this first retransmission. So what is it a retransmission? It's actually, you notice the little dot right there. So it's a retransmission of this packet, this packet here. So when we look at this, well, why was that retransmitted? Well, in this case, it was only 21 milliseconds. Why did it feel it needed to retransmit? Well, certainly it didn't see an ACK. So there's something going on there. And then if we go and we look at the next one, so what is this? This is saying it's a retransmission. But if we take a look at the sequence numbers, 229608071, that's a retransmission of this frame right here. Perhaps, actually, let me just make sure. Yeah, this one is a retransmission of this. This is a retransmission of this. Again, we didn't get any ACKs. When this thing was working, we were seeing these ACKs come back. Here's ACKs, and then here's an application level message. Here we're seeing a retransmission of first this packet and then this packet. I'm not sure why it retransmitted this one rather than starting with the first packet. Not really clear, but that's the order in which we saw the retransmission. And this one took 200 milliseconds before that was retransmitted. We can do that same thing with setting a time reference here. And we can see, yeah, so that was 233 milliseconds from that packet from the first instance to the second one. This time we do get an acknowledgement, and this is actually the acknowledgement for this frame here. So we got that one. Now notice it didn't acknowledge this one because this is not, we're missing a bunch of intermediate frames as well. So now it goes through and retransmits to come out, catch up to all of this stuff, but there's still a bunch more retransmissions that are happening. It finally retransmits this one yet again, this 5092, it retransmit yet again. And does it get an ACK back for it? Yes, it finally gets an ACK back for it. So we had to retransmit multiple times before we finally got everything back, all the ACKs back that we needed to know that we got this through. But essentially what we're seeing is we have some packets being lost. It was just this group of 1, 2, 3, 4, 5, 6 packets. All the other stuff was working fine up until then, or so it seemed. And then we go and we have another group, and we have another group. And this is a very different behavior than what we were just looking at in the first trace. So this is random packet loss, groups of packets being dropped randomly somewhere inside of AWS. And how do we know that this is AWS? It's because we're right on the edge. So we're seeing, we saw the packets going into AWS. The 10.02 is AWS. We saw the packets going into AWS. So we know that it's to the, in my thought, it's to the left side and it's not to the right side, because we saw it go in, but we didn't see X coming out. So we know that when we look at our diagram of the network, so let me go up a few. If we're monitoring right here, we know that the packet loss is on the left side of that. So, and that's true whether the probe is there or there. It's still to the left side. So depending upon where your probe is, that tells you how many things you need to look at to understand where the problem lies. But when you're sitting somewhere in the middle, you can always determine left side, right side packet loss. So we've got this left side, towards the AWS environment packet loss, and we're looking at this. So this was a fairly hard thing to look at, except for one thing. We saw this high throughput, high traffic volumes start to happen, and as the traffic volumes increased, that's when we started to see the packet loss. As soon as the volumes dropped back down, the packet loss went away. Volumes go up, the packet loss happened. So it looks like there's a bottleneck somewhere in the environment. So I'm going to switch back to our slide thing, and yeah, so trace 2. So that looks like congestion. There's some bottleneck, and it's when you tie those things together. Well, so AWS, when they first came out, all their interfaces had this thing called a VIF, virtual interface, and they basically supported about 1 gigabit per second. And you could never nail down AWS on exactly what they did. They then came out with what they called Nitro. This was about 3 or 4 years ago that they started offering this as an option. So even when you scale up to your biggest servers, you would still, out of the box, you'd only get the VIF interface, which is this virtualized network interface that worked very nicely with their SD-WAN. Well, if you needed more, on the larger ones, you had the option of a physical interface that would be dedicated to your instance. Yes, there's some virtualizations on the way to get there, but you basically could get the entire 10 gig of an Intel 82599. And then later on, they introduced this ENA, this enhanced network architecture, and that would allow you up to 25 gigabits per second. And I say up to because you needed to basically dedicate that box to it. I mean, you had many CPUs and so forth. You might not be able to get that. But when you're trying to get high throughputs, you need to be making use of what they call the enhanced networking features. And that's what this case was. So we were using the standard, actually, I'm sorry, I think we were using the Intel 82599 environment, and we needed to switch over to the ENA. So we needed to go one bump up in terms of the networking options. One problem with this that I'm going to really, I think it's a problem, is that the packets were being dropped, and we could go to AWS and they could see the packets being dropped. But our monitoring never showed, so there is no packet drop on the interface. It's not a metric that we have visibility out of the box from AWS. So instead, it's only when we see it happening in a real world in a trace, or somehow on the application we need to detect that. Applications don't really detect retransmissions. They detect slowness. If you're not getting the throughput that you expect, then you might need to looking at packet traces to see this. So that's exactly what we had to do. We had to go and get packet traces. We then worked with AWS and they said, oh yes, we can confirm that we were dropping stuff in either in the VIF or in the 82599 environment, and you needed to move to a bigger size. But the amount of convolutions you had to go through to get the right people at AWS, because it's not an out-of-the-box analysis that they do. They certainly don't provide it to the customers. So you need to have something like a packet trace analysis to be able to show that you're dropping packets as you get to higher throughputs. Do the calculations yourself and see if you're there. And if you just look at your throughputs and you see that you're getting close to 10 gigabits per second and your performance is leveling off, that might be your issue. Okay. So now I'm going to switch over to trace number 3. See what we got there. Okay, I'm going to go through the same process. I'm going to look for the flags. Total flags, only 19 flagged packets out of 4,000 packets. How about retransmissions? 4. If I was looking at traffic going over the internet, or traffic going over my Wi-Fi segment, I had 4 packet drops out of 4,000, with retransmissions. I'd say not a problem. Move along. There's nothing to see here. There's nothing to see here. I mean, those kinds of packet loss you see all the time, especially when you're going through public environments. But remember, I told you I'd like to go and look at the IO graph. And look at that. So even with only 4 dropped packets, at least measured by my interface, there was something else. Yes, it's it is spiky. It's it's a bursty environment, but we never really. I mean, well, down there, I guess we went down to close to 0 packets. Maybe 5 or so packets per second. But now we go and we have a sustained 0 packets for 20-some seconds. How could this be? So this actually is a case where even this small amount of flagged packets, these duplicate ACKs and the retransmissions, even that small amount, our DPI probe did point it out, but this is one we had to drill into really, really tightly because it was the application monitoring that said we had a big problem. So how can this be? How can retransmission, if we got this big giant ass outage, how come we don't see more retransmissions? So let's just take a look at that. So what is the flow? Who is the client? Who is the server? What is the traffic flow? So if I'm looking at this, I'm just looking for a break here. So I'm seeing, okay, I've got one direction, then another direction. So I see the large packets, 1348, 1348, 1348, 1348, with an ACK, 1348, 1348, 1348, 1348, ACK, 1348, 1348, and a little bit. Oh wait, and some more. So this is mostly data coming from the cloud and being acknowledged. And every once in a while, you'll see, I'm not even sure if I'll be able to just sort of glance at it and see. But for the most part, this is data just coming, this is one-way data coming from inside AWS and going out. So by sitting here with my little monitor sitting on the edge, when I'm looking at this, if stuff stops coming, I'm not going to know that there's a problem because I'm not going to see any retransmissions. Because yes, there may be retransmissions. He's not getting the axe when this incident happens. Let's find that particular incident. So it's true that there's not axe, but let's just look at the last time we see data from that one. I'm just eyeballing that, and I'm going to set my time reference. So this is the last data segment I see before there's a 21.9 second period where we hear nothing from there. And actually the last packet that we saw did trigger duplicate axe. That wasn't actually the last packet. So there were some packets that were lost right as it was going down. It was a little bit problematic. And then we start to see the data coming from it. But now we're seeing a whole bunch of duplicate axe because there was one of those packets right at the very beginning which was missing. So it's the duplicate axe that are the biggest piece of the puzzle right here. And not seeing any traffic for 20 seconds. I'm going to tell you something. Our DPI probes, and most of them, they aren't looking at 1 second granularity. Usually, you're talking about 1 minute or higher granularity. So yes, we see a throughput drop when you're looking at 1 minute granularity, and we did see that, and we see a spike in retransmissions, but the retransmissions are very low. But you needed to look at that duplicate axe piece to see more. So you need your DPI probe to be smart enough to look for duplicate axe as well and do something with them, so that will also generate something so that you'll know. So when we go through this thing, yeah, we had some retransmissions, and look at this. Even while we were doing those retransmissions, there was a jump here, 5 seconds. Notice I've got 2 time columns in here. One which was, when I started out, this was showing clock time, wall time. Another, and I changed it. That I can easily change by looking at the format from time of day, for instance, to looking at it by seconds since beginning of capture. And then I have another one. Now what is this? What is this field looking at? So that one, sorry, shouldn't be clicking on that. That one is looking at the time since the previous packet. That's our TCP time delta right there. So with our TCP time delta, we also see that there was still, even before it finished before it got the retransmission done, there was another 5 second gap. It was actually, till the time we caught up, that was a 27.2 second outage before we finally got the missing, we had a retransmission there, so we had all of this, but we're finally started moving along 27.28 seconds here. So this is a pretty significant outage, even though the metrics, those flag things I was talking about, the retransmissions, the duplicate axe, weren't very large in magnitude. Total of, I don't remember very long, a total of 20. And some of those were even before the period that we're talking about or after. So we're only talking about the 16 or so flag packets that were an indicator of essentially a 27-second network interruption. And let's look at that on our graph. So, okay, there and there. So I'm not sure what was happening with that, why that IO graph was not working. But when we look at this and zoom into it for more detail, so this is that initial 22 second outage, and then it was another 7 seconds there to bring it to 27 seconds before it actually. So there was a little burp while it got sort of caught up, but then it didn't finally fix itself until 22 and 30 point something seconds. So this was really quite a long network outage, the instance obviously didn't go down. You know, it was still trying to talk there. It was actually trying to retransmit, but the packets it was sending were not getting to their destination. In this case, getting routed outside of AWS. All right, I'm going to stop for a second and take a look at. Yeah, remove the time reference. Maybe. Yeah, I probably should have tried that. That may have given it. That may have broken it. That it was wrapping. Maybe it was wrapping the stuff with the two overlapping time references. It started back from 0. Is there any way to tell if the outage was from a noisy neighbor VM? And there's not an easy way. So that this would be probably for that first one or this one. Is there something that caused it to go down? And so maybe, but I don't care, because if we're not able to talk to our EC2 instances because of something else, then our environment is not protected. So I don't always have the answers, but let me go on in the presentation and say, so once we see these issues, we get packet traces so we can confirm it. So just the fact that we see a blip on our DPI probe, that's not enough. We need to take our due diligence, 2-3 steps further and get packet traces that show, because if it's talking to, say, a client who's in I don't know, New York City, maybe the problem's in New York City. So we need to look at the trace to figure out, is it on a left side or right side issue, and maybe we're going to take some new traces that are even closer. So get those packet traces so that we can verify that it's inside the cloud. But then what do you do? Because this is why we're here in the first place, which is we want to have visibility to the network inside the cloud. So what do we have to do? We have to actually open a ticket with the cloud provider, AWS, GCP, Azure, what have you. And we need to give them the details. And I'll tell you, don't just sit there and wait for them to call you back and then try and talk them through it. Put as much details as you can. If you have packet traces, put them into the ticket, because if not, you're not going to get the right level of person who's going to be able to deal with this. So give them the details that needed. And by the way, they don't know, they're not experts in collecting packets. You're the expert in collecting packets. So you need to tell them, where did you get this? If you did the capture inside their environment, was it a VPC port mirror? Was it collected on an instance? Was it collected on an interface directly connected to the Direct Connect? Yes. So was it on the Direct Connect interface? Where did you get this data? So put that in there as well. And don't assume that they know how to read a packet trace. So put little arrows in there, like this thing. Oh, this is the last time. Well, let's go back to this one. Here's the last time I heard from your device, and we didn't hear from it again until 9.4 seconds later. Put that information in there, because when you have those details, share it with them. If the first tier guy doesn't know how to interpret that, he's going to bring on the right level guy, or hopefully you'll get them quickly. So what do we hear back? So I have to say, we usually don't hear something back immediately. That's just the reality. Even for some of our, especially if it was a transient thing, they're going to look into it and maybe get back to you. If you've lost a high priority application and it's happened multiple times, you need to get an answer quicker. You may not be able to wait for that. One of them is, they took a device out of service, and that was the routing time to reconverge after removing it due to taking the device out of service. And they didn't think it would impact anything. We saw, there's a failure to a particular availability zone that affected Direct Connect links. This actually, after we see these things, then those kinds, might even show up in alerts that they send out to their customers. The one about our interface was too small. You need to upgrade the network interface on your particular instance. But what you don't want is that other one on the bottom. We were unable to determine the cause of the issues that you were facing. So that's disappointing, and you want to avoid that as much as possible. And from dealing with these types of issues for a while, it's important to be insistent. Say that you saw this problem, you're able to prove that it was inside the AWS environment. And once you build up those things and you build up, and they start to trust that the data that you're getting is true and accurate and reflects outages that are affecting your applications, and it has an impact on those, then they start then the prioritization of this starts to go up, and they assign this to people who actually can see into that. A lot of times you're working with the people who are assigned to the role of interfacing with the customers, and not with the people who are working on the engineering and the operation of especially the network environment. I got some more questions. In a real-time environment, are the packets captured so they can be looked at if any incident happens? Yes, after a fashion, so not always. So that's a goal, but it's not you don't spend so much money to set up these monitoring and visibility environments to capture every packet for every potential incident. You want to identify what are your critical components and make sure that you have the resources that you need for them. Any way to show packet comments as a column? I don't know. Talk to the Wireshark guys. I'm just a user like you. If you capture in the AWS environment, do you bring traces out to run Wireshark? Oh yes, absolutely. Yep. Yeah. So for production environments, we're not running Wireshark inside our production environments. We're using other tools to capture data in there and offloading it and doing it there. So yeah. So yeah, I do the analysis. A lot of times I'll do it on my laptop. And we also have some analysis environments inside our network. Obviously, if the data was collected with one of those DPI probes, then we can either do the analysis on the DPI probe or analyze it on another machine. So, but you're gonna need to use something like Wireshark. In most cases, you're gonna need to have this packet by packet view, not just the summarized metadata that's coming that we had, that it detected during that 1 minute for that conversation. It detected, 22 retransmissions. You're going to need to see what they are with the packet data. Show me the packets. What did I learn here at SharkFest? The packets never lie. So you need the packets really. Okay. Do we have any more questions? I probably should be marking these things. Answer. Right. Okay. Thank you. Okay. Okay. Something like that. Okay. Let's get back to the presentation. I've been going on here have I been doing this for an hour? I guess I have. Okay. Here's another example. This is a recent one, actually, October 9th, 2020. We are investigating network connectivity issues for a small subset of newly launched EC2 instances within a single availability zone, US East 1, AZ2, and US East 1 region. We have identified root cause and are working towards resolution. This is the type of thing that you might see, and that might correlate with your issues. By the way, don't always trust when they say a small subset of newly launched EC2 instances. I don't know what newly launched means to them, but if you're seeing anything that is affecting some of these servers, sometimes they may put some boxes around their description of the problem that are overly constraining and don't really reflect the reality. So if you start to see issues, starting at, perhaps before 148, because that's only when they did the first announcement, and all the way until they tell you that it's done. So take a look at the AWS Service Health Dashboard. And as I said, there are very similar dashboards, and there's RSS feeds and some other ways of getting this to be able to get alerts directly on your platforms. So take a look at those things, because they may correlate with some of the issues that you're facing. What you don't want to have happen, which has happened to us, is you report it to them and then it shows up here. Ideally, AWS should be identifying as soon as it happens, because they have the network visibility inside their environment. It's not always the case. So that's why you need to do the investigation. When you have something, please report it to them. That may help other users as well, because it might show up on their dashboard if they didn't catch it before. All right, so we got cloud. What about the traffic that doesn't feed into our DPI? I mean, we already talked about this a little bit, so that perhaps you can do some capture on the instances, but there's some other things. So yeah, third on there is you capture on the instances. Well, okay, the first one is actually redundant. Traffic, set up a traffic mirror to a collector, or maybe to your DPI. But then if it was DPI, then you're not, this isn't the answer to that question, because it was in your DPI. But traffic mirror doesn't always have to go to a DPI. Maybe you can do that to a packet collector that's going to allow you to do analysis after the fact for troubleshooting, for forensics, rather than for real-time monitoring like a DPI probe. Flow logs is another good source of data. So all three of the major IaaS, PaaS vendors provide flow logs, so that you can take a look at traffic, very much like NetFlow. I'll talk about that in a second. Capture on the instances, TCP dump, whatever Wireshark used the dump cap, what have you. And there's a lot of other network data source that go into logs, I would say. So your firewalls, proxies, internet gateways, NAT gateways, even your content delivery networks, a lot of log files that we're going to have some other data that's going to provide you with additional information to help you understand what's going on, and see what you have from provider-specific alerts that may say your direct connect link is down, or some other thing. Though, looking at an AWS environment, looking at the CloudWatch metrics that are provided for those different platforms. And I do want to talk about one of these in great detail, which is the VPC flow logs. Similar to NetFlow, you do have this 5-tuple of IP, port, and protocol, but it also has an account. So you actually can get that IP, port, protocol be seen in multiple accounts, especially if you have 2 accounts talking to each other. So you might see it twice. And it also has some security information in there, which is a little strange, but okay, we'll take it. So if something was blocked because of a security group or a NACL, you would see it show up as reject. That can help you a lot right there, because there is some security inside of there that's different from those firewalls and so forth that we were talking about. And then you have the packets and the bytes. Now, it used to be that they waited till the connection was closed and then they would throw that out, and then they started throwing out some intermediate logs. Now you can actually turn it on so you get them per minute. You can set the granularity so you get records every minute. So you have near real-time visibility with these things. So it's a lot of data. They just introduced, I say just, but within the last year they added TCP flag. So I had 10 packets. There was a SYN in there, there was a FIN, and there was a reset. That's important information. There was push bit. If you didn't see a push bit, then you probably didn't even send any data. What if you only saw SYNs but no ACKs? That probably means that you had a connection that failed. They're including the subnet, VPCs. They're also including NATed IPs. Now, this is pretty important, because as packets pass through the environment, they may have one set of IPs to get NATed to another set. So inside each account, you have the ability to have additional NATed IPs added into this VPC flow logs if you're using the latest version of VPC flow logs. VPC flow logs, hard to deal with. That huge volumes. Yes, so you need a log management system. Yes, they are captured and stored. You can look at them manually on each individual instance, but you really need to be processing them through a log management system like Elk. That's your Elasticsearch, Log Stash, Kibana, Splunk Datadog, or a SIM if you're on the cyber side. That can right out of the box, you can very easily get some throughput monitoring. It does have security pieces in it because of the NACLs and security group rejects. And I suggest that if you're going to be taking the trouble of processing this, that you associate it with your applications and location information so that you can get extra value out of that. And I also went one step beyond that, and I was able to infer connection failures. So even before we had the TCP flags, we could do that. To set up a TLS session, you have the three-way handshake, SYN, SYNAC, and ACK. Then you have a client hello, server hello, and two more back and forth. You need to have 5 turns at a minimum to be able to open up a connection. And then you need to send a request. And then you're probably going to need to close it if it's a short-lived one. But maybe we can. So if you have a new session, if it has less than 6 packets, you probably didn't get all the way through the setup. So here's an example of using that. So while I would love to have packet for looking at everything, sometimes we don't have that. And I need to fall back on looking at the VPC flow logs. So here's a case where we looked at connections to, yes?
We are out of time, it's 5 p.m.
Oh, we're out of time. I'm going to take 2 more seconds.
And afterwards, you guys can continue the discussion over to Discord in the Zoom one chat.
Yeah. Okay, so VPC flows, we can get connection failures from that. You can also capture on your instances, and you need some mature processes to be able to do this. I talked a whole bunch about this, and there's a lot of commercial tools, open source tools, and what you see today is not going to be the same as what you saw a year ago and what you're going to see a year from now. To which I say thanks. And now we can, if we had any more questions and answers, because I know I went through them, thank you very much. Hope you enjoyed it, and I will go and look for more questions. So for the questions, okay, are your DPI probes in the cloud or are they on premise? Yeah, yes they are. Sorry, we're really not talking about how we do this. We don't want to get into a lot of technical details here. But suffice it to say that it's not just one set of DPI. There's a lot of possible DPI probes, and there's a lot of different ways of doing it. And we have what we think is a very good solution, but it's also an evolving solution. Do we use CloudShark at all? No, we. So I think the answer is no. But there's a whole bunch of caveats to throw around there. Again, I don't think it's we don't want to go into a whole bunch of details about how we're doing things at Capital One, but we're very happy with our ability to support our high value applications and I'm in the network side. There's also people on the cyber side, and also to protect that entire environment by having the visibility that we need to this environment.